In this lesson, we are going to look at properties of tangent lines to a circle. A tangent line or tangent to a circle is a line in the plane of the circle that intersects that circle at exactly one point. Other lines that you may recognize as diameter, right? Diameter line goes from one side of a circle to another. That is an example of a chord because it intersects at 2 points on our circle. Tangent lines only intersect at 1 point on our circle. And we call this our point of tangency because that is the one and only one point that intersects along this curve. Now, a property of a tangent line is that if from the center to that point is our radius, and that from that radius is a right angle. It is perpendicular. So our tangent line will always be perpendicular to our radius. It'll always be 90 degrees. So we can actually use that information to solve some problems here. Let's look at this first example. Given this figure, I can see that ML and MN, these two segments here, are tangent to our circle, which means that they are intersecting at that 1 point. And also, because they're tangent, I actually know that those are going to be perpendicular. They're going to be 90 degrees each. In this diagram, I'm given a central angle of 117 degrees. So since this figure right here of LO, M, and N and M, it's a four-sided figure, the total angle measure of that four-sided figure is 360 degrees. So let's put all this information together. I know these are both 90 degrees. I know this is 117 degrees. So if I want to solve for the missing angle measure, I know they all have to add up to 360 degrees. So if we use our calculator, 360, take away 90 degrees, take away another 90 degrees, and take away 117 degrees, you should get x equals 63 degrees. Let's look at a few more examples. What is the measure of angle E? This very missing piece right here, this missing angle measure. Well, looking at this figure, DE is tangent to our circle. It's intersecting at this 1 point, and that means that this is now going to be perpendicular to our radius, or our diameter in this case. So if that's the case, this is going to be 90 degrees and 38 degrees, so I can solve this as x plus 38 plus 90. It's not going to equal 360 like our first example. This is a triangle, so it should equal 180 degrees. So that means x should equal 52 degrees. In this example, we have our two lines. They are tangent. So since they are tangent, they are perpendicular to our radiuses. So I can write this as x plus 60 degrees plus 90 degrees plus 90 degrees should equal 360 degrees. Where did that number come from? This is a quadrilateral. Quadrilaterals have a sum of the angle measures of 360 degrees. So when I subtract 90 degrees, and 60 degrees from 360, I should get that the central angle, written here, is 120 degrees. Let's look at an example applying our tangent lines. The CN Tower in Toronto, Canada has an observation deck 447 meters above ground level. About how far is it from the observation deck to the horizon? Earth's radius is about 6,400 kilometers. So you can see the lengths here. The radius should be the same for both of these values. The question is asking, what is this length right here from the top of that observation tower right here to the horizon? This creates our nice tangent line to our horizon. So that means this must be 90 degrees. If we're solving for the missing length, we have a missing length of a right triangle, we could use Pythagorean theorem. So the A in this case would be 6,400 kilometers squared. We don't know our B, And the C, which is always across from our right angle, is going to be 6,400.45 squared. So let's use our calculators for this. 6,400 squared, it's a really big number, plus b squared equals 6,400.45 squared. Just going to write all that out. I'm going to subtract this value from the other side. So subtract 0, 9, 6, 1, 2, 3, 4. So I'm getting b squared equals 5,760.2025. And I want to take the square root of my answer because I want to take the square root of b squared. So it's about 75.9 kilometers if we were to round to the nearest tenth. This converse theorem is just the reverse of our previous theorem of if we knew this line was tangent, then it is perpendicular to our radius. If you're told it's perpendicular to this line right here that's connected at point P, then we know it is a tangent line. So that's just saying the converse theorem. But here's an example of finding a radius knowing these other missing lengths. I know BA is tangent, so that tells me that this is 90 degrees right here. It is tangent to this radius. What if you did not know what this radius was in our circle, but you knew these other lengths in our triangle? Well, we can generally use the Pythagorean theorem because this is a right triangle. So I can write this as our c squared, right? Because this is our c squared, our a squared, and our b squared. Our c, our hypotenuse, is x plus 8, this total length, squared, plus x squared and plus 12 squared. So when I simplify this, this is 144. We have our x squared. The big question might be, where did I get this from? I just want to remind you that if you have x plus 8 squared, that's saying x plus 8 times x plus 8, where you are distributing each term into the other parentheses. So x times x is x squared, x times 8 is 8x, and then here we have 8 times x, which is another adding 8x, and 8 times 8, which is adding 64. So that's why this simplifies to x squared plus 16x plus 64. Then we can subtract 64 from both sides. But also we can move this x squared over, and notice that these will actually cancel out. So you're left with 16x equals 80, and divide by 16 you get 5. The radius has to be the same for both. Let's look at this example. If I'm going to use my Pythagorean theorem to solve this problem, I know that the hypotenuse is x plus 6 squared. I'm going to say that this x is our a and the 10 is b. So I'm going to write this as x squared plus 100 equals, well, x plus 6 squared, I'm going to do it off to the side here. It's going to be x squared. X times 6x is plus 6x. 6x. And then the last terms here is going to be plus 6 times 6, which is 36. So this simplifies to x squared plus 12x plus 36. Notice how there's an x squared on both sides. If I were to subtract, well, they get eliminated. So I'm going to move this 36 to the left. I'm left with 64 equals 12x divided by 12, and 64 divided by 12 is 5.3%. repeating. I'm just going to round it to 5.3. Our last theorem with tangent lines is that if two tangent segments to a circle share a common endpoint outside the circle, like right here, then the two segments are congruent. So if I know AB is tangent, BA and BC are both tangent lines to our circle, and they both share this common point, I can actually say that these two segments are congruent to each other. So let's take a look at an example. In this example, if I know that these lines are tangent to our circle, I actually know that if this is 10 centimeters from A to D, then that's the same as from A to F, meaning this one should also be 10 centimeters. If I know that the length from B to D and BE, they're both tangent, they both intersect at B, that means this one would also be 15 centimeters. And if I know from C to F is 8 centimeters, well, that's equal to CE, which would also be 8 centimeters using this theorem. So if we were looking for the perimeter of this entire figure, I could say 10 plus 15 plus 15 plus 8 plus 8 plus 10, and that would mean my perimeter is 66 centimeters.